Hey there, coding enthusiasts. Welcome back to Conquering the JavaScript Interview. Today we're tackling the fractional knapsack problem, as the title and thumbnail already gave away. Just like the activity selection problem, which was the last one in this video series, this playlist, it also spins around that greedy strategy, but with a bit of a twist. So we're going to imagine we have a knapsack with a weight limit, like a bag, right, that we're going to carry, and a bunch of items in front of us, whether we're like in a bank vault as robbers or in some D&D universe where we're doing a bank heist, I don't know. Let's just say there's a bunch of items in front of us with different values and weights. Our mission is to pack that knapsack to get the maximum value, and the tricky part on this one is that you can take fractions of items. If we have like a gold nugget, maybe we can chip away just enough to get the maximum value of the gold in front of us without having to take the entire brick or rock or whatever. The point is we can break items into pieces to generate the maximum value we can hold in our given weight limit. So think of it as like strategically filling our plates at a buffet to get the maximum and tastiest mix within the plate's limits before it falls apart. The problem is kind of a classic in coding interviews, testing your skills and optimizing under constraints and making efficient choices. Key abilities in any coder's toolkit. So if we're ready to dive on in and maximize our knapsack's value, then let's crack this problem open. But a reminder that there's a description in the link down below for the Covalence community membership. For $25 a month, you get access to our front end and back end courses. Combine them, that's our entire full stack program, hundreds of hours worth of content in there, as well as my Zero to Hero React course. Any other courses or course updates that get added to our offerings are automatically for free given to you in the community membership. You can also get access to Discord, so you have a better and more direct line to me, other Covalence staff and instructors, as well as our alumni that are always happy to help you on your coding journey. So if you have interest, check the description for that below, as well as the code pen for this video's prompt and the code if you want to go ahead and grab it and examine it and follow along with me, or like I always recommend, delete it and write it along with me or afterwards to the best of your ability. Even if you can't solve it or figure out what's going on, writing this by hand will help generate, the muscle memory and those connections in your mind of how this is solved and written. So, all right, folks, we're going to jump on into the nuts and bolts of the fractional knapsack problem. Like I said, we've got a knapsack. It's got a fixed weight limit. That's a big constraint. And then there's a bunch of items, each with its own weight and value, but that's where it gets interesting. Unlike the usual knapsack scenario, we can take fractions of these items. Our goal is to pack that knapsack in a way that you get the maximum total value without crossing the weight limit. It's all about balancing what you take to get the best possible outcome. So there's not really much of an analogy I can give y'all here, as it's fairly straightforward. We got items that have value and weight. We can pack our knapsack, which has a maximum weight, as much as possible without breaking the weight of the knapsack and getting the maximum value. And the trick is we can break things apart as needed. So let's use some pseudocode since there's no reason for an analogy in this video. First up, we're going to go through each item and calculate something important. Its value per unit weight. This gives us a ratio to figure out which items offer the most value for their weight. So that's going to be calculating what we're going to call a value density, right? It's just going to be an item's value divided by its weight. This is going to give it a ratio that will tell us which ones are the most important to pack into our bag. Then we need to obviously sort the items by that value density. So after I calculate the value density, we're going to sort them in descending order. I want the high value, low weight items right at the top of the list because we're going to be cramming them into our knapsack until it's time to start breaking things into fractions. Then we're going to select and add items to the knapsack. Obviously, that's where the action happens. We're going to loop through our sorted list and start adding items to the knapsack. If an item fits in fully without busting the weight limit, great, we take the whole thing. If not, we're going to grab just a chunk of it, enough to fill the knapsack without going overboard. As we do that, we're going to track a total value as we pick our items. We can also track what items we pick if that was part of the problem. I've seen variants of this where the input will be a little bit different, but the output a lot of the times is just the value. In this case, I'm going to show y'all how to not only crack the value, but also track the items that we pick, as well as any ones we had to break into fractions. And a lot of the times, it's just the value that is the output that's required. So I'll show you a little extra step in today's video. That's our plan to tackle this problem. It's a perfect example of a greedy strategy where each step is about making the most optimal choice available, a very short-term style solution. In our last video, the activity selection problem, I explored the greedy strategy and approach is all about, like I said, making the best choice. And I did it more in depth, but here's a TLDR for this video if you don't want to go watch that one really quickly, which I do suggest you do afterwards if you stumbled upon this one without watching the previous one. The greedy strategy shines in problems where making a series of locally optimal choices leads to a global optimum. It's ideal for problems like the last video and this video, the fractional knapsack, where each choice can be made based on current information without needing to reconsider previous decisions, right? So the choices I make later in this, when I'm filling the knapsack, won't affect anything I've already put in the knapsack. So that's a big, that's a big edge case you have to consider about when or not to employ a greedy strategy. So it's efficient, it's simple, and it's really effective in certain problems, right? But again, it's not always optimal. In some problems, a choice that looks best in the short term might not be part of the best overall solution. In this case, it's not something we have to worry about, but that's one of the times that you don't want to use it. AKA, it's very problem specific, right? So make sure that if you're going to be taking a greedy approach to solving something, you can understand and describe the pros and cons behind it like I talked about in the previous video. But anyway, let's start modifying and getting into this code here and writing some sleek code to actually solve this problem. This goal, like I said, is just for the CODEPEN prompt. Maybe some people stumble upon it there, so I wanted to make sure things are more specifically written in these prompts so you can have them on hand as well as the instructions. We get an array of items. Now, this is something else I will see in variations of this problem in other videos I've watched where I found it or solved it. Maybe it was like on Hank, LeetCode or HackerRank or somewhere like that. The inputs for this will vary. Sometimes you get two separate arrays, an arrays of numbers, which will be the weights, and arrays of numbers, which will be the values, and you have to make sure you track the indexes between the two arrays to calculate them. Sometimes you'll get an array of arrays, where each sub-array would be the value and weight based on their index position. So index 0 is the weight, index 1 is the value, or something like that. In our case, I'm going to make it a bit simple and give y'all a very specific structure, which will be an array of objects, and each object will have a property for you called value and weight. Modifying this to the array of arrays, which is another common way I've seen it done, is actually very simple if you see it this way, pre-written with actual properties that you can reference, aka .value, .weight, and then you would say, oh, instead of value, it's index 0, instead of weight, it's index 1, and it'd be the same solution. So again, we need to take an array of objects, as well as a carrying capacity, or the weight of our knapsack, and then all it needs to do is be a function that returns to us the value, and in our case as well, what items it takes and what fractions of those values of items that we actually broke here. So basically, it's going to be a bunch of whole items until it has to finally break one to get to our max weight limit is typically how this works. So again, we're going to be using a greedy approach, a great example of that from the last video where I went over more specifics of it and what it is, and this video as well, and I gave y'all a couple of tests, which again, I tell myself I really need to remember to make these easier to copy and paste for me during the video, but alas, it is what it is. Let's go ahead and write our function. We're going to call it the fractional nap. I keep misspelling this during my practice attempts of this video. There we go. Fractional knapsack. We're going to get an array of items, and each item is going to be an object, but remember, you could also see them as array of arrays, and we're going to have a maximum carrying capacity of our knapsack to get this figured out. So the first thing we need to do is, like I had said, calculate a value density, and then we're actually going to combine it. We're going to calculate the value density, so again, making sure we figure out which item is worth the most for its weight. And then we're going to sort them by that as well to make sure the most valuable per weight ratios are at the top of our list and the cheapest ones are at the bottom. That way our greedy approach can just take the most expensive ones right away until it's time to finally break something fractionally. So what we're going to do is take the items array, remember that's an array of objects in our case, and we're going to sort it. So like I said, we're combining those two steps of calculating the value to weight ratio as well as the sort process. So we're going to do a quick sort here. Actually, it means we're going to do a sort by using the sort method. A quick sort is a specific kind of sort that I think I have covered in my video series here. We're going to do A and B again, element 0, element 1, and element 1, element 2, etc., etc. So this represents each element we're trying to sort by. And what we're going to do is we're going to do some math here. So again, we're going to be subtracting something because we want a descending order, so the higher minus the lower, right? So what we're going to do is we're going to take b, which is an object that has, again, a property, just so we can remind ourselves. It'll be value, which will be a number, and then it'll have a weight, which will be a number. That's what each item in the item array is. So it's an array of these objects right here. Shout out to my TypeScript fans. You can already see how I'm describing code here. If you don't know TypeScript, it's okay. You should learn at least the basics so you understand and give yourself a leg up in learning other languages that are statically or strongly typed. But yeah, this is the structure of what we're looking at. An array of objects of these properties, and they'll have numbers as their values right there. Okay, so b.value divided by b.weight. That is the value to weight ratio of element B. We're going to do the exact same thing for element A, which gives us a.value divided by a.weight, and it sorts it in descending order. So our highest weight ratio items are up, weight to value ratio item, or value to weight ratio items are up top, and our least are on bottom, right? So remember, sort is an in-place method, meaning it's going to mutate the items array, but we don't really care about preserving the input. In this case, I'm just going to go ahead and let it sort itself out, pun intended. And that is our calculation and our sort in one go. So like I said, we're going to be tracking our maximum value in this case, starting at 0, and as we add items to our knapsack, we're going to be updating this value. And again, this is an optional tidbit that you don't always see in variants of this problem, but I'm going to track all my items that I'm adding to the knapsack and their fractions if that's a requirement, or you want to show off in your interview that you say, hey, not only am I going to track your maximum value for you, I'm going to tell you what's in the knapsack and which items are whole and which items are fractional, as they have to get broken and added. So we're going to do this as an additional step here to keep things kind of fancy, right? Righto. So here we go. What we're going to be doing is looping through our items. And again, if you can help it, use shorthand to give yourself an easier time. We're going to say const item of items, right? So instead of saying let I equal 0, I is less than items.length, I plus plus. I don't care too much about the index of each item in this case. I just care about what each item is, again, in my sorted array of items by their cost, by their value to weight ratio. So we're going to loop through using this convenient shorthand, and we're going to make a decision. Like I said, we had to make a decision of, do we still have weight available in our capacity? So meaning, have we hit our maximum capacity yet or not yet? So we're going to have to do a decision, because if we haven't, we have room to work with, and it's time to push items into the array. Otherwise, if we don't have it, it's time to calculate a fraction, right? So if we have the room to work with, there's no weird fractional calculation. It's just take the item, put it in the knapsack. Remember, this is a greedy approach. As soon as we sorted the most bang for our buck, so we'll greedily just say, okay, just start cramming in. As long as we have capacity, keep cramming in these high value items. Otherwise, we're going to have to calculate the fraction. So this is, we got space, so cram it in, is that pseudocode right there. And this is, we gotta break this item up. So that's where our fraction logic comes in. So here's what we're looking at for if else. This is actually fairly easy. If this item's weight is less than our, or equal to our current capacities, right? So we're going to be updating our capacity over time, so it's not some static check. We're going to simply subtract what our leftover capacity. Sorry, I was pulling a cat hair off the microphone there. I don't know why, I just didn't think to leave that for later. But okay, yes, so we're going to be updating our capacity as we go along. So here's what we're going to do. First things first is, hey, we have an item's weight who is not going to break our capacity in this regard. So what we're going to do is take our max value and update it with the item's value, because we are about to cram it on into the knapsack. So we need to track the value, or our max value we've gathered so far, by adding this item's entire value to the max value. Then we're going to update our capacity, like I had mentioned, by subtracting this item's weight. So this is how we're going to be tracking had we gotten to our max capacity yet or not. So we're going to add the item's value to our max value, subtract the item's weight from the capacity. So on the next iteration, we can check to see if that item's weight will break it or not. Then, like I said, in this optional case, in this particular way I'm solving this, we're going to go to the fractions array and push in an object. Stop it. We're going to push in an object that will have, let's see. Yeah, well, obviously, we're going to do like this. We're going to say, hey, we did not need to break this item into an entirely separate fraction. We are just going to say, hey, it is a full fraction right there. It's the full thing right there because we're not breaking anything apart. This is, again, meant to track what we've pushed into to get our maximum value and if we had to break it up at all. So if we don't break anything up, it's 100% whole or intact, aka that's a 1. Anything less than a 1 would represent the fraction of how much we've broken apart. And the item would be what we're looping through or what we're pushing into our knapsack. So there we go. That's how we're going to do it. We're going to say this is the item. This is how much of a fraction, if at all, we put in there. And there you go. That's all we got to do. We got space, so cram it in is now technically done. Now, we have to do the exact same logic in this else statement down here. We got to break it apart. So we're going to have to calculate its fraction, meaning how much can we break apart to get to our capacity, update our max value, and also push it into our tracking array, which we've called fractions in this case, right? And then we have to say, hey, we've had to break this thing apart, which means we're probably out of capacity. So rather than updating the available capacity we have left, we're simply going to stop the loop and return, right? Speaking of which, I made the mistake in the last video and did this as well. I'm always pretty cognizant about making sure my return statement is here so I don't accidentally not return something and fail a test, for example. So in our case, let's return an object, and that object is going to have two properties: the max value we've calculated and the fractions that we have been putting into our knapsack or the items we have stored or something like that. So there we go. Now, like I said, we got to break the items up. So how do we do that, right? I'm going to say const fraction equals, take our current available capacity, and we're going to divide it by this item's weight. What this does for us now is it calculates the fraction of the current item that can be added to the knapsack. So basically, this lets us say, hey, this item's weight, or the capacity we have currently left divided by this item's weight, gets us a fraction of how much we can break off this item before our knapsack hits its final capacity. So that's what that fraction calculation does for us right there. Now that we have that, here's a trick we have to do with the max value, because we have to say, hey, we now know how much we need to break off of this item so we can take it with us. But its max value is going to be a little bit interesting, right? Because we can't just add its item value, because we need to know how much is that value of the bit we got to break. So what we get to do here is we get to multiply it by that fraction. So again, this calculates how much we have to break. How much we have to break times its original value tells us what our broken value is comprised of. So remember, this is how much we break, and the value times how much we broke is how much that fraction is worth based on its own, based on its whole value, right? So that's all that's going to do for us. And then from there, we've tracked our max value. We've already at capacity now because this is how we got to the else statement in the first place. So that tells us that we are then going to add this to our fractions array by saying fractions.push an object where we had item and fraction. So we can do a ES6 shorthand instead of doing :1 because that was the full item. In this case, whatever that calculated value is will be good enough, and it'll tell us how much of that item it had to break off in order to get its max value without exceeding our capacity. So that is our else block. There's our return. Like I said, if we have any items left in the array, we do not have any capacity, hence why we got to break this for loop, break out, return these values, and there it is, folks. We got it figured out. I'm going to save some space here so I can see this all in one line. There we go. I was trying to cram this all into view here, so if I start talking about like my outro and whatnot, or some pros and cons, blah, blah, blah. I just wanted to make sure everything was at least mostly visible on one one screen. I can always zoom out and look at it. But yeah, that's it on all its glory, crammed into one thing minus the return statement. But yeah, I think y'all got the idea. So let's go ahead and do some of my tests here to see if it works, because we do have it done. So I'm going to grab this first list of items and a capacity of 50. So let's just go down here. It should be simple. If I just console log fractional knapsack, I'm going to call it. We had a full weight of 50. I'm going to paste in my array format. Let's go verticality. All right. So fractional knapsack with this array of objects with a knapsack weight of 50 is giving us an expected output of 240, right? So let's see if that works. Save. Yeah, let's go. Max value 240. So it looks like my terminal, my commander terminal, doesn't like me console logging nested objects. That's fine. It should be these. I mean, the max value is correct, and that's the more important part. And the most important thing is, okay, we get a fraction of 0.67 for the last item, which there's the 0.67 we're looking at right there. I just haven't rounded it down. That's another good thing you can take into consideration to bump up your beginner to more intermediate level answers by doing some to-fixed and parse floating around here in order to give yourself some cleaner looking outputs. Will be nice to consider here. But yeah, we do indeed have the items and their fractions, right? So we should have two whole items. It's two whole items and one fraction at 0.67, which is what this is to get 240. So that is indeed a correct answer. This one next here is a capacity of 10. So let's go ahead and console log fractional knapsack, capacity 10, array first, comma, format, paste, max value. Again, looking like we should probably add some to-fixed logic here. Now I'm thinking about it, but we should get a 166.67, which is what this would round to. That looks good to me. And we get... so this was the interesting one. Yeah, that's right, because it had one item. As you can see here is our input. We have one item, which is very valuable, but by itself, the one thing is already over our capacity of 10. So we have to break off 0.3 of it in order for it to fit into the capacity of 10, right? Because that would be our weight right there, right? Because if we have 30 and we break off a third of it, that is 10, whatever the unit is, 10 pounds, 10 tons. I don't know. Who cares? I mean, we should care about units, but in this case, we don't. So, yeah, that's how you get to our capacity of 10. So that makes sense. Doing a 0.3 break off, and that will get us our value right there. So that's pretty dang solid. And then finally, our last one is all this big old array with a weight of 50. So let's see if we can do this here. Console log fractional knapsack, weight 50. Previous to that is the array, paste, comma, format. Let's go. There's another array of objects with a weight of 50. Max value 340, 11.5. Max value 340. That test checks out. We get an item fraction 1, and then a fraction of 0.5 as our last item to get our max possible value with our greedy strategy. And there y'all go. That's what I'm talking about. Like I'd mentioned, if you wanted to make this a bit cleaner, it's straightforward, but not as straightforward as you would think. So if you wanted to make the outputs look a bit cleaner, there is a little thing we'd have to do here. We would go down to max value, for example, and we could do to-fixed 2. Because max value is max value dot to-fixed times 2. So if I now save that now, we can see our outputs. Oops. Our outputs are now string. So remember, .toFixed is a string representation of a number in fixed point notation. So either you would have to do a to-fix or some kind of math round or something similar like that. But that gives us a nice representation with our decimals right there, 1.67, as you can see around it, and it's a string representation. If you wanted to do that to the fractions as well, you could do that. I mean, I guess we could do that. Meaning what I could do over here is to calculate this fraction, I could also store it as a to-fixed 2 to get my rounding, but then we have an issue. We have some calculation problems, or we will, because that is now a string. I want to make sure that this calculation down here specifically doesn't use the string fraction, and instead we're going to parse to a float to get our floating point decimal numbers here, right? That is just to make sure that our calculation uses numbers and doesn't do any kind of implicit coercion issues like you might have in JavaScript, just to be careful. Then from there, I would just say that for calculating for description or display purposes, I would just make this also a 1.00 so that it looks consistent. Our output looks consistent with the rest of what we're looking at here, right? So just making sure our output one is a number and the other are two fixed strings, for example. So if I wanted to take the two fixed route, I would make sure all of my outputs were string values of 2 decimal notations here of a 2 fixed 2, just to make it all look the same. So yeah, just for some food for thought right there. If you want to make the outputs look a bit more streamlined and clean here. But yeah, that is the solution, right? So hopefully the explanation of the lines as I wrote them makes sense. This one took me a little while to figure out myself. To make sure I could understand it and explain it here on video as well. We've tackled the problem using that greedy approach. I hope you found it as intriguing as I did. And don't forget to hit that like button and subscribe for more coding adventures. Your support means a lot and helps keep us making content that can help make a difference in our coding journey. So if you got questions or insights to share, drop them in the comments down below. I really love reading people's thoughts and ideas. Remember, every problem has a solution, and sometimes it's just about finding the right strategy. Keep coding, stay curious, and I'll see y'all in the next video.